In section 7 of chapter 6, we want to extend the ideas that we've been looking at for hydrogen atom to the case of atoms with more than one electron. And we also want to introduce the idea of electron spin. And once we get both of these ideas in place, we'll be in good shape to understand the structure of the periodic table, as we will see. So let's first look at orbitals. Remember, my definition of an orbital is that an orbital is a solution to a one electron Schrödinger wave equation. So in fact, the orbitals that we've been looking at, sp and d and f orbitals, are solutions for the hydrogen atom, and they are not solutions for the Schrödinger wave equation for any other atoms. So if we want to look at helium or lithium or carbon, think about organic molecules or biochemistry, these orbitals are not the right descriptions of the shapes of the electron regions. What do? Well, we could go back to the drawing board and resolve the Schrödinger wave equation for each atom that we want to look at, but it turns out that solving the Schrödinger wave equation for multi-electron systems is extremely hard to do. It's a complicated computer calculation, and it's not amenable to using for estimation purposes. That is, it doesn't give you real insight into the shapes of things. So what we're going to do is what we often do in chemistry. We're going to make approximations. We're going to use the same orbitals that we've been using anyway. The s, p, d, and f orbitals we're going to use for carbon, and after we use them for a while, most students actually probably forget that they're not actually the true solutions, they're just approximations. We're going to continue to use them because they're convenient to use. We know their shapes, we know their properties, and they do have the correct shapes. We can show that. The main difference in multi-electron atoms is that they have different energies in multi-electron atoms than they would for the hydrogen atom, and we do need to understand how the energies change when more than one electron is present. So here's a comparison of energies. It's not a direct comparison, so this is an energy scale on both of these plots. It's not meant to be the same energy scale, so they're not lining up this way, but just show the correct ordering. So for hydrogen atom, this is this side. For hydrogen atom, for one electron, the energy we know looks like this. In the yellow box, the energy depends only on the quantum number n, the principal quantum number. So for example, all of the orbitals that have principal quantum number 2 have the same energy. We call that degenerate orbitals. So the 2s and the 2p have the same energy because that L value that determines s versus p does not play a role in the energy equation. Likewise, all of the n equals 3 orbitals are degenerate. They all have the same energy. Doesn't matter if it's 3s, 3p, or 3d. All the same energy because there's no L in this equation. However, in the case of multi-electron, which is over here, now each of these orbital subshells have different energies. It is still the case that orbitals in the same subshell are degenerate, so all three 3p orbitals have the same energy, but now the 3p subshell has a different energy than the 3s, and the 3d has a different energy than the 3p. In general, for multi-electron atoms, we see that for a given quantum number, principal quantum number n, the energy of its orbitals increases as we go from s, p, d to f. So we see s is lower energy than p is lower energy than d. Here for the 4s, the s is lower than the p, the d would be up here, the f would be up here, in that sense. Now if we look at the orbitals, they have the same designations, the same quantum numbers, the same shapes, and the same orientations, but different energies. If we compare the energy ordering across all of the subshells, the subshell energy ordering goes in this order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. And at first blush, it does seem kind of confusing. Seems like there's not much of a pattern here. But we do have a mnemonic device called the Aufbau diagram, which will help you remember the correct energy ordering. draw all possible s orbitals in one column, and then in the second row, draw all possible p orbitals, subshells rather, in the second column. Starting with the third row, draw all possible d subshells in the third column. And then just draw arrows, and the energy ordering goes head to tail. So 1s, 2s, 2p3s, 3p4s, 3d4p5s, 4d5p6s, etc. So this is a handy way of remembering the correct energy ordering, and I'm going to show you an even easier way to remember the energy ordering of subshells later on. Now, the big question is why? Why does, for example, the 2p subshell have a higher energy than the 2s? It has to do with the one electron atom or ion energy. If we go back and modify our energy for a one electron system, so looking at hydrogen atom, helium plus, which only has one electron, lithium 2 plus, which only has one electron, the energy for such a system depends on the atomic number. And this shouldn't be a big surprise because the atomic number, remember, tells you how many protons are in the nucleus. So if you have a bigger positive charge in the nucleus, it stands to reason that the electron is going to be more strongly attracted to that bigger positive charge. Positive charges attract negative charges. That's essentially what determines the energy of these subshells. But the trick is, when you have more than one electron, the outermost electrons have electron density, this smeared out fog of electron density, in between them and the positive charge in the nucleus. So they end up feeling what we call an effective nuclear charge, Z effective, which is the true nuclear charge reduced by some amount, where this S stands for screening. Sometimes we call it shielding or screening. This is just due to inner electrons in between the outer electron and the nucleus blocking some of that attractive force and reducing the effective attraction to the nucleus. We can see this in detail if we go back and look at our radial probability functions. This is one reason why those are useful. Here again is my plot of the S, P, and D radial probability functions. We've seen this plot in the last talk. But here I can explain why it is that an electron in a 3D subshell, right, this is the red one, this peak here, so electrons spend most of their time around this distance because this is where they're most likely to be according to this plot. But look at these humps of electron density in between this peak and the nucleus. This is electron density due to the 3s orbital. Here we have a peak of electron density due to the 3p, and those regions of electron density that are closer to the nucleus effectively shield the charge of the nucleus from an electron that is out here in this 3D subshell. So these plots can help us understand why it is that S electrons spend more of their time really close to the nucleus and hence have a lower energy. They're more attracted. P electrons are a little bit less close than an S, but closer than the Ds, so they have the next highest energy. And then 3Ds have the next highest energy. So hopefully that helps explain why these subshells have their different energies. Now we need to look at electron spin. So the fourth quantum number, it turns out that electron spin is also quantized, and it took a while for scientists to realize this. Some of the evidence for the presence of this quantum number includes the fact that if you look closely, those atomic bright line emission spectra really consist of very closely spaced pairs of lines rather than individual bright lines. And in 1921, Otto Stern and Walter Gerlach did a very, very famous experiment in which they passed a beam of silver atoms through an inhomogeneous magnetic field, and the beam split into two separate beams as it went through the magnetic field. Now really, a silver atom has one unpaired electron in it, so this is equivalent to passing a beam of electrons through the magnetic field. And the point is, it splits into two beams, not three, not four, And it doesn't stay just one beam. There's something about the electrons that causes a different interaction with magnetic fields. This is an important experiment that led to really our understanding of the periodic table, and Otto Stern won a Nobel Prize for it in 1943. And then theoreticians Uhlenbeck and Goodschmidt proposed that electrons have some sort of intrinsic angular momentum property that they call spin, and this spin is quantized. So m sub s stands for the spin magnetic quantum number, and it can only have one of two values, plus 1/2 or minus 1/2. And you can kind of think of that as an electron spinning on its axis in one direction or the other, creating a little magnetic field that either points towards the North Pole or towards the South Pole. This is a little bit misleading because it really doesn't have a classical analog. You can't write down a classical equation that describes electron spin in any way. This is a purely quantum mechanical effect, and in fact it's actually an offshoot of special relativity, so it's pretty hard to derive. Now these spins over here, let me just write something. If m sub s is plus 1/2, we call that an up spin, and if it's negative 1/2, we call that a down spin, because these quantum numbers really are the projection on the z-axis of the angular momentum. One's pointing up and one's pointing down, and we tend to represent the up spin with a single barbed arrow pointing up. That represents an electron with an up spin, and a down spin is a single barbed arrow pointing down, and we'll use that later on. Now, with this idea that electrons have spin, Wolfgang Pauli in 1925 proposed the following principle, and it's, again, very hard to overemphasize the importance of this. This is the key to understanding the periodic table, and it's a hard and fast rule for electrons. In a given atom, no two electrons may share all four quantum numbers. So, for example, if they have the same value of the principal quantum number and the same L and the same m sub L, remember these three define an orbital. So if they have the same values here, we say that the electrons are in the same orbital. If that's true, then they must have different values of m sub s. And since there's only two possible values of m sub s, plus 1/2 or minus 1/2, it follows that an orbital in an atom can describe at most two electrons at the same time, and if it does, they must have opposite spins. Pauli won a Nobel Prize for this in 1945. Again, this is the whole basis for the structure of the periodic table, something that is hard to overemphasize because the periodic table is so important to our understanding of chemistry, and it all comes down to the Pauli exclusion principle, and I'm going to show you how that works in a later talk.